Okay, in the last class we are discussing about the temperature control of furnace. So we have discussed about connection details. Now if I come for the program, so we are using this port A as output port, port C lower as output port, this is input port, this is output port, this is output port. So what is the control register for this? So if you want the control register in IO mode, this is for port C lower. So port C lower, this is port C lower, we are using as output port. So this will be 0. This is port B. Port B also you are using these two pins, output port 0. This is mode selection for port B. I am using mode 0. This is port C upper. Port C upper is this one. We are going to take this as input port. So 1. This is port A. Port A we are using as input port 1. Mode selection for port A. I am taking 0, mode 0, and this is for IO mode, this is 1. So it will be control word 9, 8, 9, 8H. So how to first load 9, 8H into controller register. After that the process is this right bar you have to make as a low to high transition. You have to wait until INTR bar is equal to 0. Once the INTR bar is 0, then you have to read the digital equivalent of this temperature. Then I have to compare with 30 degrees and 60 degrees. If it is less than 30 degrees, you have to on the heater, and if it is greater than 60 degrees, you have to on the fan. So for that you have to write the program. So 98H AL comma 98H out control register address is FFH comma AL. Then move AL comma 00, then out. So this right bar is connected to port C lower, right? This is port C lower, right bar you have to make as 0 to 1 transition. So port C address will be FEH AL. This will make PC3 which is equal to WR bar low. Then again have to make high. Move AL comma PC3 you have to make high, means PC3 bit will be PC0, PC1, PC2, PC3, the MSB of the lower nibble. Okay, so that means it will be 08H. Is it clear? This is PC7, PC6, PC5, PC4, PC3, PC2, PC1, PC0. This should be 1, remaining all can be zeros. This is 0 hexadecimal, this is 8, 08H. Then out onto the same port C FE. So this will make PC3 is equal to right bar, these two are connected, is high. So this low to high transition will start the conversion. Then you have to check for the end of conversion, because the microprocessor is a faster device. A to D converter will take some time to convert. So once the conversion is over, this INTR bar becomes 0. INTR bar is connected to PC7. This INTR bar is connected to PC7. So, you have to input port C. In port C AL comma port C address is FEH. Then PC7 is MSB bit. So, MSB bit will be, you have to check whether this is 0 or 1. Rotate left accumulator RLR AL comma 0 1. So that the MSB bit will come on to the carry flag. This is PC7, which is the status of INTR bar. If this is 0, jump on carry. If this is 1 means carry, that means conversion is not yet over. Okay. So, you have to wait here itself. You have to input this again, jump on carry up. So, you have to continuously monitor this PC7, which is equal to INTR bar if this is equal to 1. If INTR is equal to 1, it will go to up. Is equal to 1, go to up. Means conversion is not yet over, you have to wait in a loop. If INTR bar is 0, so this will come out of the loop, then you have to read the data. So, where this digital equivalent of the temperature is available in port A, so you have to write in AL comma port A address is FCH. So, after this instruction, AL will contain the digital equivalent of temperature value. Temperature value in hexadecimal form. Now, you have to compare this with 30 degrees, the hexadecimal equivalent of 30 degrees, hexadecimal equivalent of 60 degrees. 30 degrees yesterday we have calculated, this is 4CH and 60 degrees 97H, 4C and 97. So, 4C is correspond to 30 degrees, 97H is correspond to 60 degrees. Compare AL, which contains the present temperature value, then 4CH, the lower limit. Jump on less than. If AL is less than 4CH, means no need to on the heater. If it is less than 30 degrees, we have to on the heater. Okay. Less than, we have to if jump less. So, this is true if temperature is less than 30 degrees. Then you have to on the heater, jump less than, heater on. Okay. So, heater on, you have to write the program. Otherwise, you have to compare AL with 97H, which is correspond to 60 degrees. Jump greater than fan on. Otherwise, if it is greater than 30 and if it is less than 60, okay, so you do not have to on and off fan and heater, right. So, you have to unconditional jump to monitoring this up. They repeat, you can call as, you have to repeat the process. So, where should be this repeat? Again starting from this repeat. So, you have to continuously again monitor this, you have to start for the conversion, then you have to check the end of conversion, the same process will repeats. So, at this heater on, you have to write some program, fan on, you have to write some program. Okay. Heater on, heater is connected to, this is the pin, PB7 is connected to heater. Okay. So, PB7 you have to make as 1. To make PB7 as 1, move AL comma ATH. You have to output onto port B, FDH, out FD comma FDH comma AL. So, this will make PB7 as 1, which is connected to the heater. PB7 is equal to 1, implies heater is on. Then how to unconditional jump, and how to repeat the process. Jump to same repeat process. And fan on, move AL comma, fan is connected to PB 0. PB 0 means you have to make it 0 1. AL comma 0 1, so that PB 0 becomes 1. Out FDH comma AL. So, these two instructions will on fan. Then unconditional jump to again repeat. This is the program which controls the temperature and maintains the temperature between 30 degrees and 60 degrees. Okay. For the connections given here. So, these are the connections. So, you have connected this digital equivalent of temperature to port A, start off conversion to PC3, end off conversion to PC7, and heater to PB7 and fan to PB0. If want display the temperature value, so whatever this digital value that you have read, we can apply through BC to 7 segment decoder or directly to the 7 segment decoder, and you can display the values. Okay. So, we can do this in a similar another way also. Instead of using this both heater and blower or fan, we can use only single heater only, or you can use the fan only if I use D to A converter. So, the setup will be, this entire setup will be same. I will just write from the connections of ADC onwards. So, alternative way is alternate technique. This is the furnace. So, I will use only either fan or heater. This is the sensor, temperature sensor, and I will use this signal conditioning, I will call as signal conditioning. I will give to A to D converter. This digital equivalent value are giving to some of the ports of 8255. This is same as the previous thing. This start off conversion, end off conversion is similar. This is right bar. This is INTR bar. This is port A. This is PC3. This is PC7. Now what I will do is, I will connect this another port, say port B. This I will connect to D to A converter. this output through resistance, it will convert into the voltage. This I am going to give to the fan. So, the remaining connections of this A to D and D to A converters I am not showing, because those details I have already discussed in the earlier lectures. Now, the basic principle here is everything is same except for this that. So, we will read here in port A the digital equivalent of the temperature. So, here we do not have the limits now. So, I do not want to control between 30 degrees and 60 degrees. I want to maintain at a particular temperature only. Okay. So, based on this I want to maintain a fixed temperature. So, whatever the value that we are going to get here, if this is FF means temperature is large. So, I want to reduce the temperature. For that what I will do is I will complement this, I will take the ones complement of this one. So, that it becomes 00H. This I will give to the D to A converter. So, you will get 0 volts. So, thereby this 0 volts will off the fan. On the other hand, if this is 00H, 0 digital equivalent is 00H, means temperature is almost 0. So, I will again take the ones complement of this one. So, that it becomes FFH. This I will convert into DAC, we will get the maximum voltage plus 5 volts, and this will run the fan at highest speed. Of course, this can be 5 volts to 220 volts, we are going to have relay 5 volts to 220 volts, it will operate 220 volt relay. Fan is on, fan operates at maximum speed. Because temperature is less, this is 00, or otherwise we can have the reverse. This will be fan has to be operated at, so no need of this complement also, otherwise if this is heater you can call as, instead of fan you can use the heater. So, the heater operates at the maximum temperature. Highest voltage, thereby it will produce more heat. So, instead of this I am using the heater. This is the process. So, you can write in a similar manner the program. The program is previous program only. The only modification is here after reading this temperature value in AL, okay, simply you have to complement this value and you have to give that value to the digital to analog converter. So, up to here the same I am writing the remaining program. So, in AL you have to complement this value, not AL. If temperature is highest, then heater will be operated at low voltages. If temperature is low, then you have to operate the heater at highest voltages. That is why you are taking not AL. So, this AL contents will be complemented. This I have to send on to D to A converter. So, this anyhow AL is there. So, move AL is there, you have to out onto D to A converter. I am going to connect to this D to A converter. I am connected to port B. Okay. This you have to program as output port. Anyhow, in the previous example also you have programmed the port B as output port. So, out port B is F DH comma AL. Then you have to do this repeat process, jump onto repeat. So, just we are just complementing this AL value, the temperature value we are giving to the port B, which is connected to the heater. So, thereby heater temperature will be controlled. So, which controls the temperature of the furnace. This is another way if I want to use both A to D converter and D to A converter. So, in a similar manner you can have lot of applications, like if you want to use DC motor control, a motor control using (8086). So, you can use a motor this is connected to tacho generator. So, this produces a voltage which is proportional to the speed of this. Okay. If this is 1600 RPM speed, here it will generate 40 volts AC voltage with the tacho generator. So, this 40 volts is a high voltage which cannot be directly connected to microprocessor. So, what you have to do is you have to step down this voltage using step down transformer. Then you have to connect to a precision rectifier. To convert AC into DC, because this is AC, here the voltage will be depends upon this number of turns. If I call this primary voltage, here this voltage is 40 volts in this case. In general, if I call this as V1 and if I call this as V2, and this number of turns here are N1, number of turns here are N2, then V2 by V1 is equal to N2 by N1. If I take V1 as 40 volts, in this case if it is 40 volts, and if I take this turns ratio as N2 is equal to, if I take N2 number of turns here are 5, N1 the number of turns here if I take 40, then what will be V2? V2 is equal to V1 into N2 by N1, which is equal to V1 is 40 volts, this V1 is 40 volts here, 40 into N2 is 5, N1 is again 40 I have taken. So, that you will get 5 volts. So, here we will get 5 volt AC. So, to convert it to DC we will use precision rectifier. So, the precision rectifier will be same as this ordinary rectifier, except for that here we will be using op amps. So, we can construct this rectifier by using just simply diodes also. So, if it is a half wave rectifier, 2 diodes, full wave rectifier, 4 diodes. So, the name precision is if I use this op amp, operational amplifier, then it is called as precision rectifier. Without operational amplifier also you can construct this rectifier using just simple diodes, that is called just rectifier. If you use op amps also, it is called precision rectifier. Then this 5 volts will be given to A to D converter. So, it will produce the corresponding digital value. Okay. This will be given to 8255. So, here again write bar, interrupt bar. Whenever A to D converter is connected, this is 0800, then these two signals you have to connect. So, this 8255 another port of this one we can use to control the speed of this motor using some feedback mechanism. We set some value here, set point. So, we want to operate at some speed. If it is more than that one, we can activate a. So, we can activate here some sort of brake or something like. So, we can control the speed of the motor. So, similarly, I will discuss one more example before going for the other interfacing devices, is electronic weighing bridge. So, these are all actually this minor project type of thing. So, if you want you can do these projects. Okay. So, the hardware details I have discussed here. So, only thing that you need is some sort of the signal conditioning like precision rectifier. So, you can refer any linear integrated circuits book, you can find the circuit of precision rectifiers. If any amplifier is required, amplifiers also you can find in any linear integrated circuits books. Okay. So, electronic weighing machine. So, here basically I want to weigh it. Here basically I want to weigh a vehicle. Okay. There will be 4 load cells. These are 4 load cells. So, vehicle will sit on these 4 wheels will be placed on these 4 load cells. So, below this there will be some sort of this type of mechanism. So, there is a cantilever beam, if a load is placed on this one, if I place a load here, what happens, this side is fixed. So, if I connect here strain gauge, so this load will changes the dimensions of this cantilever beam, thereby the resistance will changes. Basically here resistance is proportional to the weight. That change in resistance can be measured by using bridge. So, here we have 4 different load cells will give 4 different changes. So, the basic circuitry here will be, you have to connect these 4 in 4 arms of a bridge. This is load cell correspond to 1. This is 1, 2, 3, 4. So, without any load, this will have some resistance, depends upon R is equal to rho L by A. Rho is the resistivity, L is the length of this rod, AL is the area. If I apply some load here, so this resistance will changes. I will set the other 3 arms R. This resistance is equal to resistance without load. This R is equal to resistance without load. So, this also will be having initially without load cell application, this is also R. If I apply the load here, what happens, this becomes R plus delta R. So, when this is also R, this bridge will be balanced if I connect these 2 points to some voltage. at these 2 points you will get some voltage which is equal to 0 volts in case all are 4 R's. This is R, this is R, this is R, this is R, because this voltage will be V by 2, this voltage will be V by 2. So, the difference becomes 0 volts. If I apply the load, this becomes R plus delta R, which causes the unbalance of the bridge. Thereby the voltage here will be other than 0. So, this delta V volts that is generated here is proportional to the load. Whereas in case of this electronic weighing machine, we will be having 4 such loads. So, these 4 voltages will be having 4 such bridges. So, we will be having 4 such bridges. This is one bridge, this is one bridge. So, inside this bridge we will be having this circuitry. So, 4 such bridges. This is bridge 1 correspond to this load cell, bridge 2 correspond to this load cell, bridge 3 correspond to this, bridge 4 correspond to this. So, these 4 voltages you have to connect to the adder. You can implement the adder circuit also using operational amplifier. You can find this circuit also in any one of the standard linear integrated circuit books. You have to basically add this. Still this voltage will be very small, this delta V will be very small. So, that small voltage we cannot directly apply to this microprocessor. This voltage of this adder can be applied to the amplifier. So, I am connecting here, this is A point, this is A point, there is a link between these two. So, you have to connect to amplifier. Normally here we will use instrumentation amplifier, which will be having high gain, high CMRR, common mode rejection ratio, because while measuring these voltages there may be some interference, the common mode signals such as noise, which can be eliminated if your amplifier is having high CMRR, common mode rejection ratio, high gain, high input impedance, so that the loading effect will be less, low output resistance. So, these are the some characteristics of the amplifier that is to be used in the signal conditioning circuitry. Choose this amplifier gain such that, so the output will be in the range of 0 to 5 volts, which we can directly apply to the A to D converter, then to the microprocessor. Then this will be connected to ADC, which is connected to 8255, which in turn connected to 8086. This is start off conversion, this is end off conversion. Okay. This is the complete block diagram of electronic weighing machine. So, we can write the program. The main contribution here is interfacing the A to D converter and how to start the conversion, how to end the conversion, how to read the digital equivalent of this load. Okay. So, the program that we have used for the temperature measurement is almost same here also. So, in a similar manner you can write the program of electronic weighing machine, and if you want you can display the weight of that particular vehicle. Here we are going to lay the vehicle. So, the weight of the vehicle can measure. You can display on the display board. This is the vehicle. Okay. So, like that we have plenty of applications of 8086 using this 8255 ADC and DAC. Okay. Now, we will discuss some more the peripheral devices. Till now we have discussed about only one peripheral device, which is 8255. Okay. There are some other peripheral devices which will be having some other applications. Okay. So, the next peripheral device is 8254, which is programmable interval timer. This is 8253 or 8254. The pin configuration is same, but 8254 is compatible to 8086. 8253 is not compatible. So, this is basically a 24 pin IC which will be having 3 timers. And 3 16-bit counters. So, there are 3 control signals for each counter. One is clock 0, gate 0, out 0. This is counter 0 signals. Similarly, for counter 1 we have clock 1, gate 1, out 1. These are all counter 1 signals. Counter 2 similarly. Clock 2, gate 2, out 2. So, any IC will be having VCC and ground. And there will be one chip select signal. And there is 8-bit data bus D7 to D0. Then we have A1 and A02 signals which will select the counters. Then we have read bar, write bar. So, total 24 signals. This is 8, 9, 10, 11, 12, 13, 14, and these are total 9 plus 1, 10 is 24 pin. So, this is 24 pin IC. Basically, this programmable interval timer will be used in real time applications. To generate accurate delays. Using the delay programs, we cannot generate the accurate delays, but there are some applications where we have to generate the delays precisely, very accurately. To generate the accurate delays, we have to use 8254. Okay. In addition, this also will act as counters. So, this 8254 will act as counter as well as timer. We have both the applications. Okay. So, if you take inside this pin diagram, 8254 architecture diagram or block diagram, so you have database buffer, this is internal bus. This is internal bus. There are 3 counters as I have told. This is 16-bit counters. Counter 0, counter 1, counter 2, There are 3 signals, 2 input, 1 output. Out 2, gate 2, clock 2, out 1, gate 1. What are the functions of these signals? We will discuss. We will discussing about the different modes. So, we will discuss the functions of each of these signals. Out 0, gate 0, clock 0. There will be a data bus transfer. So, how 8-bit data bus, as I have told, D7 to D0. Then we have read write logic. For this block we have chip select signal A1, A0, read bar, write bar. And there is one control over register which is similar to 8255. To program this counters, timers, we need a control over register. So, this control register will control all the counters. There will be connection to all the counters. This is the complete block diagram of 8254 timer. So, here also we have 9 signals here. This is 8, 17 signals, 18, 19, 20, 21, and we have VCC ground. So, total 24 signals. Now, here you can program this. There are 16, 3 means 16-bit counters. We can count this using BCD count or binary counting. And you can program this as a timers also. So, the timers can operate in 5 modes. I will explain each mode in detail. So, now to operate this in 5 modes, and whether this is a binary counter or BCD counter, there we are going to, these are all 16-bit counters, this 16-bit, but you can also use as a 8-bit counters also. Okay. In case of 8-bit counters, so we have to load only 8 bits only. In case of 16-bit counter, first you have to load the 8-bit lower order 8 bits, then higher order 8 bits. Okay. So, these are all depends upon the format of the control word register. So, the format of the control word register is similar to the 8255. We have 8-bit control word register. Here also we have 8-bit control word register. Which is, this will be SC1, SC2, SC1, SC0. This will control select counter. SC stands for select counter. 0 0 means counter 0, 0 1 means counter 1, 1 0 means counter 2, 1 1 means it is illegal operation. Okay. Similarly, we have RL0, RL1, RL1, RL0, read or load either byte or word. So, byte means again so lower order 8 bits or higher order 8 bits. So, depends upon the status of these 2 pins, we can select either lower order byte or higher order byte or both the bytes. Okay. I will explain the function of that. Then we have 3 modes. In order to select the 3 modes, we require 3 control signals M2, M1, M0. There are 5 modes. So, in order to select these 5 modes, we require 3 control signals M2, M1, M0. Then this will be last bit, which is BCD, total 8 bits. So, if this is for BCD count, this will be 1, for binary count this will be 0. Okay. So, the XOR functions of this one, if I come here, the MSB 2 bits SC1, SC0, as the name implies, select counter operation. 0 0 means counter 0 will be selected, 0 1 means counter 1 will be selected, 1 0 means counter 2 will be selected, 1 1 is illegal. These are about the first 2 bits. Next we have RL1, RL0. So, the operation is, we have 4 combinations. Zero zero means counter latching operation. I will discuss this, what is this counter latching operation while discussing about the modes. 0 1 means it will read or load lower order byte only. Means for 8 bit operation, lower order 8 bit only. If this is 1 0, read or load higher order byte only. If this is 1 1, read or load lower order byte first, then higher order byte. High significant byte, low significant byte, high significant byte. It will read both, means this is for 16 bit operations. Okay. And M2, M1, M0 is mode selection. As I have told, there are 5 modes. And this is 0 0 0, mode 0, 0 0 1, mode 1, X10 is mode 2, means this can be 0 1 0 or 1 1 0, both are mode 2. This is X11, this can be 0 1 1 or 1 1 1, is mode 3. Then we have 1 0 0, mode 4, 1 0 1, mode 5. Here these 2 are don't case. So, we have 2 possibilities for mode 2 and mode 3. And then the last bit is BCD. If this bit is 1, BCD count. If this is 0, binary count. This is about the controller register. Now, how to interface this 8254 to the 8086. After that, how to operate in 5 modes and how to generate the precise delays and how to generate the square wave and different waveforms, that we will discuss in the next lecture. Thank you.